next model of computation is push-down automaton. Having seen finite automaton, regular sets and its limitations, let's look at the next model of computation. In this model, we have an input tape. Similar to finite automaton, it can only read a symbol. On reading a symbol, it can stay in the same state or it can move to a different state. It can move exactly one cell right and read the next symbol. In addition to the input tape, it has something called stack. It is also known as push down store in the literature, wherein it can store a symbol or a couple of symbols inside the stack. And as far as stack is concerned, it is allowed to perform these two operations, push and pop. So essentially, push down automaton, PDA, is something like finite automaton plus stack or push down store. This configuration we find in finite automaton. In addition to the finite automaton configuration, we have a stack or a push down store where it can store one or more symbols and it can also pop. So when it performs push as well as pop, it does some computation. In terms of state, we remember what that computation is. Okay. Remember, we have shown that a power n, b power n is not regular, and then a power p, where p is prime, is not regular, and then we have shown languages like a power n, b power 2n, equal number of a's and b's. Now, what we will do is, let's look at couple of non-regular sets, all are non-regular, and see whether these non-regular sets are accepted by push-down automaton. In the sense that, can this stack increase the computational power of finite automaton? By providing stack to finite automaton, are we increasing the computational power of finite automaton? Meaning, some of the languages not accepted by the finite automaton, can it be accepted by the this machine, which is finite automaton plus stack or push down automaton? Okay, so that's precisely the focus. Let's look at the first case study. The language is a power n, b power n, where n greater than or equal to 1. Let's check whether this language is accepted by the push down automaton or not. Remember, it's a machine. So as we defined before, there is something called transition function. Let's describe the transition function for PDA if exists. So let's look at the logic first. Suppose the string is this, and it's a valid string, a cube, b cube, it's part of the language. So we should design the machine in such a way that when I reach here, I should somehow remember the number of A's read, so that when I start reading this, I can compare whether number of B's read is same as number of A's read. So essentially what we will do is, we will associate for each B one A the matching is perfect, which means number of A's and number of B's are one and the same. So how are we going to translate this into push down automaton? Here is how we do. When I read A, what we will do is we push some symbol. Say let me push capital A onto the stack. So to start with, let's assume the top of the symbol is Z0, and essentially the stack contains exactly one symbol called Z0. Okay, and when I say push, then what will happen? A will come on top of it. So this will be like start symbol. Now when I read, then I move right. You are not allowed to write on the tape. That provision is not there. If at all there is a write, then it is only in this stack. Then we move right and we read the next A. What we do, we perform again push operation. Then the stack will become AA. Then we move right and then we read this. Again perform push A. Then it is like this. So essentially, when we start reading A's, we perform push. Now I start reading B's. When we start reading B's, what we do, for this A, we pop this. For this A, we pop this. Which means for each B, we pop one symbol out of the stack. Okay, we perform pop. So finally, we reach the start symbol, which means number of A's read and number of B's read are one and the same. So what is the configuration? You are at a state where input tape is empty and stack contains Z0, which means the start symbol, which means it's a valid input. Meaning input tape is empty and stack is also empty, but because we add Z0 as the start symbol, stack as only Z0, which means it is a valid input. Correct? Now let's look at input like this. Say 4 A's followed by 2 B's. For the first A, we perform push. For each A, we perform push. So we get 4 A's onto the stack. Next, we start performing pop. So for this B, we pop this. For this B, we pop this. So finally, if you look at the stack configuration, it will be Z0 followed by AA. Now what is the configuration? Input tape is empty, but stack is not empty, or rather the stack is not containing just Z0, it is also containing some more A's. Correct? Which means such a configuration is invalid. Let's look at this case. Say 3 A's followed by 4 B's. Now for this input, if you look at the stack configuration, for 3 A's you will have this. Then we start performing pop. And for the first B we pop this A. For the second B we pop this A. For this B we pop this. Now what happens? The control will be pointing this. Input tape is not empty, However, stack is empty or stack contains Z naught, which means for this B you do not have corresponding A on the stack. That shows that this input is also invalid. So essentially, with the help of this stack, we see when we start reading a B, do we have a corresponding A on the stack or not? If we have a corresponding A, we pop and we say it is valid. And finally, you reach a configuration where input is empty and stack contains Z naught, then it's a valid configuration. If you find excess A's, which means when you stop, you will see that input tape is empty, but stack contains couple of more A's. And in the case where number of B's are more, you see that input tape is not empty, however stack is empty. Okay, so these two are invalid. Fine. Now, whatever we have described now, we are going to formally write using the transition function. Just like finite automaton, one can come up with a transition function, one can come up with a transition diagram, and there are other representations as well. There is something called context-free grammar. All that we shall discuss. Please note, just to mark the end of the symbol in the stack, or we have reached the bottom of the stack, we use the marker or the start symbol Z naught. Okay. To say that stack is empty, we should know the stack is empty, or that can be indicated by using a symbol, which is why we call this symbol as start symbol. Or to say that we have reached the end of the stack, this symbol will be of use. Fine. And it can only read one symbol at a time. There is no write in the tape. And after reading a symbol, it can stay in the same state or it can move to some other state. And whenever it reads a symbol, it can move exactly one cell right. There is no left move, there is no right. The only additional feature is something called stack, wherein it can store one or more symbols. That will, in some sense, will help us to understand what was the task done at this point in time. And meaning, in some sense, we remember the number of A's read through this stack as far as this example is concerned. Okay. Now, just like finite automaton, let's explore a couple of more case studies and understand the limitations of this mission and see what can be computed, what cannot be computed, and subsequently we move to the next model of computation. Okay. So let's explore the formal representation, which is the transition function. Let us describe the mission. Now, delta of, we start from Q0 and we read an input symbol A. Now, we should also bring the stack configuration as part of the description. To start with, it will be Z naught, which is why I've included Z naught as the start symbol, so that we would be able to describe formally what the automaton is doing, right? Otherwise, describing empty stack would be difficult. Instead, we say the start symbol is Z naught. So what we say is, if this is the configuration, we say we go to a state, say Q1, and then for this A, we push a capital A, and then below that you see Z0. So we always write top two symbols of the stack. This is top two symbols. In some cases we write more, but as of now this represents the top two symbols. What was there before was Z0, and on top of it we have placed A, and from Q0 we have moved to Q1 on reading A with start symbol being Z0. Now we are at Q1. When we are at Q1 we read A. Now, which means what? Stack is already containing A, so top symbol is capital A. Then what we say? We say Q1, we stay in Q1 itself. For this A, we push 1A. Below that there is 1A, so you get to see this. So which means with this we read the first A, and with this we read the remaining n-1 A's. Now I am in Q1, I read a B, top of the stack is A, which means I need to perform pop. Let me go to a state Q2 and I perform pop. When I say epsilon, this is the notation, which means pop the top symbol, in this case capital A. Now you are at Q2, you read a B, top symbol is A, you perform pop, which means this will help us to pop the first B, and with this we pop the remaining n-1 B's. Now if everything goes right, then we are at Q2, input becomes empty, which means input tape is empty, and stack contains Z0. We have reached the start symbol. We say that we accept, which means go to something called a final state. You can either say this, or we can say QF comma, even this Z0 can be popped out. Both are fine. So QF is our final state. Fine. So now this clearly tells us starting from this and subsequently we read n-1 A's, we read the first B pop, we read n-1 B's pop. Now when we reach a configuration where I am in Q2, input tape is empty, stack contains the start symbol, which means it's a valid configuration, and reach the final state, either you leave the start symbol, or if you wish to pop the top symbol as well, yes, we can do it. This is also valid. Fine. Now just like finite automaton, there are missing transitions which we need to focus on. So I am in Q0, and when I am in Q0, I read a B, and start symbol is Z0, which means it's invalid, it has to be rejected. So we say QR comma Z0. QR meaning reject state. When we are at Q0, when we read a B, it has to be rejected, so which is why we do this. When we read a A, it is valid, and so this part is fine. Similarly, when we are at Q2, we get to see A, which means when you are in Q2, you look for B, correct? But you get to see that you read a A and followed by A, then it has to be rejected, and or when you are at Q2 you read A and the top symbol is say Z0, then it has to be rejected. We don't disturb this stack. We say A remains A and Z0 remains Z0 because we know this is invalid. We immediately go to a reject state. So like that, one has to focus on missing transitions, and those missing transitions are invalid, and take the automaton to the reject state, which means what we have described is a deterministic push down automaton. For every configuration we have a unique output. We say we go to QR, or we go to Q1 or Q2 or QF. Okay, so like this one can fill in the remaining transitions.